So this is the derivatives. This is what we did in the last section. All right. What you're going to see is these are going to relate back to what happens when you take the antiderivative, obviously. It's a little bit different because if there's a number besides 1, so you see how this is a 1, it becomes an a squared. And so then you take that number into consideration when you take the antiderivative. So if you go to page 388, you will see the antiderivatives. So when you start looking at integrating something like this, where you have a number and a variable with a function, you see a square root and this subtraction here with the number and then the variable, that's going to relate back to sine. You see no root and you see addition of two squares, that's going to relate back to the arctangent. And then if you see the root again, but the function is first, and you see function on the outside, that's going to relate back to arcsecant. But you do have these little pieces here. Like if this is a 4 and an x squared, then the square root of 4 is 2. So this a is actually a 2. Think of it when you're looking for the difference of squares, and you have to recognize you have a perfect root, or even in this case, a non-perfect root. So if I were to say factor x squared minus 9, you would need to recognize that this is a perfect square and this is a perfect square, right? And that you could take the square root. That's what you're looking for here. You're looking for the fact that you could square root this and you could square root that, and you could come up with something that would fit into that piece there. So that's what you're trying to do. You're trying to back recognize these, okay? Versus when I give you a function, you take the derivative of the arcsine, you're working the other direction. Now you're recognizing this fits into the arcsine antiderivative. So these are 3 examples of some more simple ones. If we look at the first one, you could think of this as the square root of 2 squared minus x squared. And you can see that you have an arcsine situation. Arcsine, if you look back up here, is the arcsine of the function over the number plus c. So this antiderivative is going to be the arcsine of the function. My function here is just x over my number. Well, my number here is 2. And then we have r plus c. So that's what we're looking at here. That's why you need to recognize these. So for this one, you're going to immediately see the fact that you do not have a root, right? And that it's addition. So we have some function. Here's the thing. You're going to have to mix and match these. Like I couldn't do natural log because I don't have, if I had a 2x up here or something, then I could say, oh, that's the natural log of 2 plus 9x squared. Because if I had some x up here, then I could say my u is my 2 plus 9x squared. My du would be 18x, and I could do u substitution and do natural log because it's something to the first power. But I don't have that, so it's not going to derive back to a natural log here. So then I'm going to say, okay, what else has something in the denominator that is 2 things added together? That's going to be arctangent, okay? And you may be thinking, well, 2 doesn't have a root. Yeah, it does. Square root of 2, okay? So you have to think outside of integers. Whereas in the factoring world, we would have stopped at integers. We're not going to stop at integers here. We can talk irrational numbers here. It's okay. So you could think of this as dx over the square root of 2 squared plus 3x squared. All right? And then you'll see that that relates back to your arctangent. That's a number squared plus a function squared, right? And so now I'm just going to go to my arctangent and say, well, my arctangent tells me that I have to do these 1 over my a and all that. The only thing is that you have to also consider the derivative of that function. So I do have to consider this guy. When I take the derivative of 3x, what am I going to have?
3.
A 3. Do I have a 3 in there? No. So I have to account for that. Okay? I have to get rid of the 3 that's going to be produced. Right? So if I did u substitution here, I would have 3x, du is 3. I don't have a 3. How would I get rid of it? I'd multiply by 1/3. So I can multiply this function by 1/3 to get rid of it, because that's what's going to happen. Like, that's what's going to happen here. Because I'm going to have a 3 on the top here. I'm going to have a 3 there. So 3 times dx times 1/3, I haven't changed anything, right? And that's what I'm doing here. I'm just not writing out my u substitution, if that makes sense. I'm not writing it out because I don't need to, but you can. So I know that my antiderivative is going to have a 1/3 in front of it because of that 3x. And then I'm just going to do my arctangent. My arctangent says it's 1 over my a. My a in this case is square root of 2. All right, so I have a square root of 2 there. Arctangent of my function is 3x, over my a value, which I said was the square root of 2, plus c. And you can combine those, 1 over 3 square root of 2, arctangent of 3x over square root of 2 plus c.
And you would want us to get the square root at the top?
You don't have to. You can, but it's not that important. All right, look at the last one. So for the last one, I have a root, so I know immediately it's likely not tangent, right? It's either sine or secant. And you'll also notice that you have a function inside and a function outside. That indicates you're going to have a secant. Okay, so I have a root with subtraction and a function on the outside. That indicates that I have a secant, okay? So for this one, my function here is, I would think of this rewriting it. I have dx over x square root of, that's a 2x squared minus a 3 squared. So this is my function. This is my number here. All right. In this case, I have to consider the 2, right? And so when I rewrite this, my function here is missing a 2, right? I know that sounds weird, but I have to multiply the top and the bottom by 2 for that to actually work.
How do you know that?
Because my function's 2x, because this was 4x squared. So the square root of 4x squared is 2x. If I multiply a fraction, the same number top and bottom, I don't actually change it, right? You agree? If I multiply a fraction by the same, so if I say, if I have 1/2 and I multiply top and bottom by 3, did I change my answer? No, those are the same thing. So I can do that here. I can multiply top and bottom by 2. This must be a 2x for this to fit. But if I make this a 2x, I have to multiply by 2 on top. That actually does 2 things for me. If I multiply top and bottom by 2, not only does it take care of this guy right here, because this has to be the same function as that, but it also takes care of the derivative of that, which is 2.
Okay. That's why it has to be 2 because it has to be the same function.
It has to be the same here and here.
Gotcha.
Right? So I can multiply top and bottom by 2, which actually takes care of my derivative, which means I don't have to multiply by 1/2. Because I multiplied my fraction by 2 over 2. That's just 1, right? So that took care of these being the same. And up here I had to consider this 3, right? And I had to multiply by 1/3 because of that 3. I don't have to multiply by 2 because I have a 2, right? So if I did the derivative of 2x, so if I did like u substitution, u is 2x, du would be 2. Normally I don't have a 2, but because I had to multiply top and bottom by 2, it actually took care of that problem as well. So I don't have to consider the fact that I'm missing a 2, right? So once I know that piece of it, then I can just go straight to my arcsecant. My arcsecant says I'm going to do 1 over my a. My a here is a 3. That's my a. And then arcsecant of my function, which is that 2x. And they do have absolute value on this. 2x could possibly be negative if I plug in the right variable. So it is absolute value there. And then over my a, which was 3, plus c. So I'm just going back to this box in the middle of the page, and I'm just plugging in my functions and my a's. All right, so when you have e, a couple things happen. First of all, anything to a power like this can be rewritten. So if I were to rewrite this, I could say, well, really, that's just e to the x squared minus 1 squared. That is kind of like an arcsecant, but we're missing something out here. So we're going to do u substitution. So we're going to say, well, u is going to be e to the x, okay? So I'm going to do u substitution. I'm going to say, well, u is this e to the x. What is du? What is the derivative of e to the x? Well, that's just e to the x, dx, right? Do I have another e to the x? No, I just have a dx. So how do I get just the dx by itself? No, how do I just divide by e to the x, right? Will that make dx by itself? Well, what is e to the x? Well, up here I said e to the x was u, yes? So instead of writing e to the x right here, I'm going to write u. Du over u should equal dx, okay? So now I'm going to rewrite this function right here, replacing everything, okay? What was d to dx? Well, that was du over u, yes? On the bottom, I have the square root of u squared minus 1 squared, right?
Yes.
Now, if I have a fraction over a fraction, I can actually, this guy can just go in the denominator, right? So that's the same thing as writing du over u square root of u squared minus 1 squared, right? Now that looks exactly like the arcsecant. So go back to your arcsecant. That's identical to your arcsecant, right? So now I can just plug in my arcsecant. My arcsecant says 1 over my a. Well, my a here is 1, right? 1 over a. Arcsecant of the absolute value of my function. Well, here it's my function is u over my a, which was 1 plus c. And then I'm going to plug in my u. I don't really need to write this 1 over 1, do I? That's unnecessary. Arcsecant. Absolute value of my u. My u is e to the x. Will e to the x ever be negative? No. So I don't even need an absolute value there, or the 1 in the denominator, because that's also repetitive, plus c.
This don't seem too hard. Too difficult.
So this is such a simple process that people always forget. Remember, when you have a denominator, you can split up the numerators, okay? And so if I were to split this up, one of mine is going to just be basic u substitution without any special ln's or arctangents. And then the other one is going to be requiring a trig function. So this first one right here, I can really think of it as x times 4 minus x squared to the negative 1/2, right? And I can use u substitution here, right? If I were to make this my u, what would my derivative be? Negative 2x, right? I only have an x. So what do I need to multiply by? I have to divide it out. So I need to multiply by negative 1/2. Negative 1/2 and negative 2 will cancel out to the 1 that I need, because I just have a 1 in front of this, right? So if I do u substitution here, my derivative would be negative 2x, but I need it to be positive 1. How do I turn a negative 2 into a positive 1? I multiply by negative 1/2, right? So negative 1/2 will take care of this and this, right? Then I just take the antiderivative of that. How do I do an antiderivative? Well, I take my function and I add 1. What's negative 1/2 plus 1? 1/2. And then I divide by that new exponent. How do I divide by 1/2? I multiply by 2. Okay? So that's my antiderivative there. So let's write out the u substitutions. So if my u equals 4 minus x squared, my du is going to equal negative 2x dx. I only have a 1x, right? So I have to say, well, negative 1/2 times du equals x dx. Now I've taken care of it. So that's why I have that negative 1/2. And then I can ignore this piece of it because I've already accounted for it and just worry about the antiderivative of that guy. Yeah, so you can write out the u substitution if you want to. That's fine. I don't care. You're just going to have u to the negative 1/2, which is going to be add 1 to the negative 1/2. That's u to the positive 1/2 divided by 1/2. That's multiplied by 2. And then substitute your u back in, which was 4 minus x squared. So I just did that process without actually replacing my u, is what I did. So this piece I have actually taken the derivative of. Negative 1/2 times 2 is going to give me just a negative 1, right? And then 4 minus x squared to the 1/2, well, that's usually written like this. So that's my antiderivative of that piece of it, okay? Then I need to add to it the antiderivative of this guy, okay? This is a number squared minus a function squared under a root. This is arc sine, okay? Arc sine. This 2 is just like in front. So I can just say 2 times my dx over 2 squared minus x squared.
So why don't you do that for...
This is like a perfect arc sine though, okay? This is, for this arc sine, I literally can go straight here. Leave the 2 in front. Then I'm going to do the arc sine, because the derivative of x, which is my function, is just 1. So you don't have to consider the number. The number's accounted for in your antiderivative. You do have to consider if your x is anything but just x. If it's x squared, then you have to consider there's going to be a 2x, right? If it's 3x, you have to consider that it's going to be a 3 when you take the derivative. But if it's just an x squared, it goes straight to that beautiful arc sine that you're just plugging it in. So it's going to be this 2 times my arc sine. My arc sine is my function. My function here is x over my number. My number here was 2, and then plus c, and I am done with that one. So the first guy was just basic u substitution with no natural log, no arc sine, nothing. The second piece of it required an arc sine. So when you look at this one, if 2x is my function, what is my derivative of that going to be? 2. What do I have?
Oh, put that in the front.
What do I have? I have a 3. How do I turn a 2 into a 3? Multiply by
3/2.
3/2, right. So your answer is going to be 3/2 times the arc sine of your function. Technically, it's your function over your number, but your number here is 1. So you can just say arc sine of 2x plus c.
What page are we on?
We are on page 390, example 4. So when you look at this particular problem, it does not look like you have anything to go on here, all right? Here's the thing. Yes, you have to go back in your brain to like algebra 2 world, and you have to say, could I make a perfect square? So let's talk about perfect squares, right? So like x plus 3 quantity squared. That's a perfect square, right? It's always going to be x squared plus double this guy, right? 6x plus this guy squared, all right, if I factor it out. So how do I back into that? Well, if I want a perfect square and I just have these 2, I'm going to cut that guy in half, right? And square him to get this. That's how you do that. So we're going to look at just this piece of it, and we're going to group it. Can I do that? Yeah, because that actually didn't change anything, okay? The group being there or not being there didn't change anything. What I am going to do now, though, is I am going to look at this guy and say, can I make him a perfect square? Why would I do that? Because there is no other way to take the derivative. I cannot use natural log because then I have a derivative of that trinomial that is a problem. I can't use u substitution because that would be a booger to rewrite in u substitution, don't you think? Like, I have an x squared and an x. What am I doing? Subtracting, dividing by x? No, thank you, right? So I need to see if it can fit into a perfect square, to have a square and a square. So that's what I'm going to do. I'm going to say, well, I have x squared minus 4x. I'm going to make this a perfect square trinomial. How does that look? Well, that looks like cutting this in half, 2, and squaring it. So if only it looked like that, I would have a perfect square there, correct? Mm-hmm. But I can't randomly add a 4. That changes my equation. But I could add a 4 and subtract. No, you can't randomly add or subtract anything. But I can add a 4 and subtract a 4. Did that change anything? No, that's adding 0. Is that a problem, adding 0? Does that change an equation? No, it does not. So I can add a 4 and subtract a 4, and then all of a sudden I don't have a problem. Okay? So I took this group, I added a 4 and subtracted a 4. And then I have a plus 7 there because he was already there. Does everybody see what I did? So how does that help me? Well, my dx doesn't change, right? I can rewrite this. I can rewrite this to the factored form, right? The factored form of that looks like this, x minus 2 squared. Yes? Negative 4 and positive 7. What does that give me? 3. Now, in pre-calculus world, we would probably say that doesn't have a root. But the truth is, everything has a root, right? May not be a perfect root, but everything has a root, okay? So this is dx over some function squared plus some number squared. Everybody agree? Mm-hmm. Which one of those gives me a function squared plus a number squared? Which of your 3? Look at page 388. So I do need to double check and make sure this derivative is okay. What's the derivative of this guy? It's just 1, so he doesn't affect anything. So I can literally go straight to my arctangent. My arctangent says I'm going to go 1 over my number. This is my number, square root of 3. And then arc tangent of my function, this is my function, x minus 2, over my number, which is square root of 3, plus c. And that is my answer there. Same conceptually. It actually has the rest of it. I didn't have that down there. If you look below it, it says it's also bounded by the x-axis and the lines x equals 3/2 and x equals 9/4. That actually tells me that this is a bounded graph. So I'm not going to have a plus c. I'm going to plug in numbers, right? So they actually want me to do a definite integration here. So we are doing definite integration. All right. So once again, we have a potential for completing the square. All right. If I'm completing the square, I'm going to cut this guy in half, right? And then I am going to square it. That's how I complete the square. All right. So a couple things here. My x squared is a negative here. So when we do this completing the square, it's going to look a little different because I'm going to end up adding and subtracting on the other side of it. It's a little bit different than if you were to do it without doing this, but here. So you end up going, if I were to complete the square right here, pull out the negative here and write it x squared minus 3x, right? That's all I did. I just pulled a negative out, factored out a negative. So then when I complete this square, it's going to look like this, minus 3x, cut that in half, 3/2, plus 9/4, right? That's just 3/2 squared, right? Everybody see that? And they wrote it in your book, so we'll just write it like they wrote it in your book. They did 3/2 squared, right? Minus 3/2 squared. So I have all of that. Everybody see that? I added and subtracted. Here's the thing. This is a minus, and it's in the root. Okay, it's in the root. So I'm going to end up with a function and a number, which needs to come first. So look back at your little things. If you'll notice, if I don't have a function on the outside, which in this case I do not, then we're likely trying to get it towards a sign, right? The sign is the number first, then the function, okay? So if I were to pull this guy out, I have to pull him out as a positive. Why? Because there's a negative right here, okay? So if I take him out of the parentheses, I have to go ahead and distribute that negative sign. Does everybody understand what I'm saying? He is currently in the parentheses. It didn't matter before because the whole parentheses was not negated. So taking him out of the parentheses just meant multiplying by 1, okay? Here, I am going to take this guy out of the parentheses, but he's going to turn into a positive 3/2 squared because of this guy right here, not the subtraction. And then we still have the subtraction there for the group. How would I write this group now in factored form? Well, that's just going to be x minus 3/2 squared. So does everybody see how I went from this to that? So this right here is a -1. I factored out a -1. In order to take anything out of the parentheses, I have to multiply by what's in front of the parentheses to get it out of the parentheses. So it was originally the subtraction. I pulled it out as a positive because in order to take it out of parentheses, I have to go ahead and do that multiplication. Everything else is left in the parentheses, so it's still under the -1 that's outside of there. Okay, does everybody understand that? So now I have from 3/2 to 9/4 of 1 over the square root. All of this stuff is still in the root, okay? 3/2 squared minus x minus 3/2 squared. This is an a and a u. This is a squared minus u squared, okay? That's what that is, which is sine, by the way, a perfect sine. And the derivative of my function is still 1. So I don't even have to consider anything that's going to affect it because it's still a 1. So once I get to this point, I can go straight to my arc sine. And I can say the arc sine then of 1 over my number. Oh, yeah, no, function over my number. So x minus 3/2 over 3/2 from, and I don't have to do plus c because it's bounded, from 3/2 to 9/4. Normally I would say simplify that, but what happens when I plug a 3/2 in? It's a 0. So it's gonna work itself out when you plug these guys in. So I have 9/4. If I plug in my top guy, I have 9/4 minus, this is 6/4, right? So I have 3/4 over 3/2. So I'm just plugging these guys in. 9/4, we'll do it out here, minus 6/4 over 3/2. That's just going to be 3/4 times 2/3. That's going to be 1/2, right? So I have the arc sine of 1/2 minus the arc sine of 0. Okay? What angle gives you a sine of 1/2? It's a 30-degree angle, right? Or also known as pi over 6. So this right here, this is going to give you pi over 6. What angle has a sine of 0 on the unit circle? Where's your y 0 on the unit circle? Yeah, 0. So I have pi over 6 minus 0. My answer is pi over 6. 0.524 if you plug it in. So this, believe it or not, this is what we have learned all of these. From basic derivatives down to these arc sine, arc tangents, which are kind of hard to see there. Here's the thing. You cannot rely on getting the same type of problem every single time, right? So start with your path of least resistance. By that I mean, if you can just use your U substitution, or if you can just use your exponential rule, don't be looking for arc sine of something, right? If you can divide it out, let's say you have a function over a function and you can use long division and get it into simple ones, do that, right? Everything's not going to be the most difficult way, okay? Everything's not going to be an arctangent. So you have to make sure you're looking and saying, oh, this is just a natural log. Or, oh, this is just a basic U substitution. Everything's going to cancel out nicely and be U substitution. You have to look for path of least resistance to the most difficult ones.